has to do with Supplemental Problem 3.9. You can find this problem in the ECE302 ebook in the Chapter 3 Supplemental Problems, starting on page 11. In our last video, we modeled the inverse active region. Take a look at modeling what's called the inverse saturation region, where I'm going to forward bias both the base emitter and base collector p-n junctions, but I'm going to have a negative collector emitter voltage. Let's go back to Chapter 3 on page 16 and look at these curves again. I'll be operating somewhere along here and operating along this line over here. What's true about our transistor under these conditions? Well, we have a voltage across the base collector that's a fixed value of V sub BCR on. The base current is greater than or equal to 0. The collector emitter voltage is now a constant V sub CER set. The collector current is less than or equal to 0. And then one more condition. We had this from the Ebers-Moll model. What I want to argue is that when you're operating along here, you have an inequality. You have less than or equal to beta R. Let's go back to our supplemental problem and see if we can argue that. These are the conditions we just flagged. Now if you go back and think about what we're doing here, I'm calling the collector the emitter and the emitter the collector, and the base is the same. If this was a problem when we're in the first quadrant, this would be the collector current, the emitter current, and the base current. And in our Chapter 3 notes, we argued that the ratio of I sub C to I sub B was less than or equal to beta F when we were in saturation. What is this current now? This is minus I sub B, and beta R is the beta F of the third quadrant. Now, if you don't like that, you can also derive the following. You could start out here that if I sub B were to decrease, we're going to go down in this direction. What's going to happen? Well, because of the minus sign here, I sub C is going to be increasing. And you can carry that backwards and show that the inequality goes back this way. These are the things that are true about my transistor. Can I build a model that covers all of these? And of course the answer is no, it can cover some of them. This is obviously a battery and this is a battery, so between the base and the collector I've got a battery of V sub BCR on, and between the collector emitter I've got a battery of V sub CER sat. Current in this voltage source can be positive or negative, and likewise for this one, and the ratio doesn't have to follow any relationships. We assume inverse saturation, put the model in, and we'll have to check that the base current is greater than or equal to 0, the collector current is less than or equal to 0, and that the ratio of minus IE to IB is less than beta R. What about the PNP transistor? We should draw it this way again with the emitter on the top and the collector on the bottom. But in our original notation, this is the emitter and this is the collector and this is the base. So we're going to still follow that notation. We're again going to be forward biasing both p-n junctions. The conditions are the same here. We're just going to change the subscript. We're going to change the direction of all the currents. Go this way, go this way. This one's coming in, this one's coming out, this one's coming out, this one's coming in. The model is the same, it's just flipped upside down. Do the same checks, we can guarantee these voltages, but I can't guarantee the currents in a voltage source. I need to check for the inequalities. It'll be the same as the NPN case because we've turned the currents around. Check that the base current is greater than or equal to 0, the collector current is less than or equal to 0, and the ratio of minus IE to IB is less than beta R. Let's do an example. Consider this one transistor circuit with an NPN transistor, two 1K resistors, 5 volt battery, and now a 3.2 volt battery. Could you find the current I and the voltage V if we had a base collector reverse turn-on voltage of 0.72, a collector emitter reverse saturation voltage of minus 20 millivolts, and a beta R of 4? Assume that we're in the inverse saturation region and then check your assumption. The first step is to put the model in. Between the base and the collector we have a battery of V sub BCR reverse, which was 0.72, and then between the collector and the emitter, we've got V sub CE reverse saturation, which is a minus 20 millivolts. Let's go around the loop this way. The rise in voltage is 5, the drop is IB times 1K, 0.72, and then a minus 0.2, and then 3.2. And I can solve for I sub B. It'll be 5 volts minus this quantity. This turns out to be 3.9 on our side of the equation, a minus 3.9, then divide by 1K, and you get 1.1 milliamps. Collector current is the current in this resistor, and that's going to be the voltage across here divided by 1K. So what's this node voltage here? Well, it's 0, and then we take minus this node voltage, so a minus 20 millivolts, and then minus 3.2 volts divided by 1K, and that's minus 3.18 milliamps. The emitter current is the collector current plus the base current. Add these two up, I get a minus 2.08 milliamps. And now the ratio of minus I sub E to I sub B, change the sign on this to 2.08 milli, and then I sub B was 1.1 milli, we get 1.89. I sub B is greater than or equal to 0, and the collector current is less than or equal to 0, and then minus IE is equal to 1.89 times I sub B, so it's less than 4 times I sub B. The assumptions check. We can solve for I and V. I is I sub B, and that was 1.1 milliamps, and the voltage V is going to be the negative of this voltage, so it's going to be I sub C times 1K, but with a minus sign. We had that I sub C was a minus 3.18, so the two minus signs cancel. And we get 3.18 volts. And this is supplemental problem 3.9.